In this short appendix video, I wanted to recall some of the basics of topology and topological spaces. So at ETH, this is a third semester lecture, but I mean, maybe your third semester is already a while ago. And also in algebraic geometry, the way that we apply topology focuses less on the open sets, as it's usually done, and more on the closed sets of the topology. So here is the definition of a topology in terms of these closed sets. Given a set X, a topology on X is the data of a set curly C inside the power set of X. So curly C is a set of subsets of your space X, which is called a set of closed sets in the topology. And it should satisfy that both the empty set and the entire set X are closed. And this set curly C is also closed under arbitrary intersections. So if you take an arbitrary intersection of closed sets, it's still closed. And if you take a finite union of closed sets, it remains to be closed. And then complementary to this, a set U in X is open if it is its complement is a closed set. And then this pair of X with this collection of closed sets is called a topological space. As I remarked at the beginning, often a topology is specified by a set of open subsets. And it just turns out that in algebraic geometry, it's more convenient to specify the set of closed sets, and we're mostly going to follow this language. And just if you want to translate to the usual thing, the usual axioms tell you you get a set of open sets, which contains the empty set, the entire set. It's closed under finite unions, and it's closed under arbitrary unions and finite intersections. And then if you take the complement in all of these axioms, you exactly get the axioms A, B, C at the top. And so with the basic definition settled, I just wanted to recall some of the constructions that you can do with topological spaces, and wanted to start with just some examples of topological spaces. The kind of minimal topology with respect to inclusion on a set X is the trivial topology, where the only closed sets are the empty set and the entire thing. Then on the opposite side, there is the finest topology, which is the topology with the most closed sets possible. And there you just take the closed sets to be every subset of X, the entire power set. This is the discrete topology. Then, kind of importantly for our lecture, there's the cofinite topology. And there the closed sets are, first of all, any finite set in your set X is a closed set. And then you also need to include by hand the entire set X. And this turns out it's a short exercise to verify that this indeed satisfies all the properties of a topology. And these were kind of very generic things. They function for all set X. But then to have like one of the more usual topologies here, the Euclidean topology on X, which is R to the N. And there we specify the open sets. The set in Rn is open if and only if for each X in this set, there exists delta greater than 0, such that the small delta ball around X is still contained in U. That's the classical definition of the Euclidean topology on Rn. Okay, so these were some examples. And then we're often going to use in the lecture some constructions which start with one topological space and then produce another one. A very basic thing in this direction concerns subsets of the topological space, because when you're given X with the data of a topology and then any subset, there's two operations which you can do. One is you can take the closure, which is denoted A bar, and one definition of this is that you can take the intersection of all y inside X closed containing A of y. And the second characterization is this is also the same thing as the smallest closed subset of X with respect to inclusion, which contains A. And the reason, for example, that this is a closed subset just follows because this curly C is invariant under taking arbitrary intersections. So this immediately shows that this is a closed set, and you can convince yourself that this is also the smallest closed set containing A. The second is that from topology on X, on this subset here, you also get a subspace topology on the set A, and there the closed sets inside A are just those subsets B of A, such that there exists a closed set Y in the bigger space X, such that B is the intersection of A with Y. And in the particular case, when A is actually a closed subset of X itself, then you can check that this simplifies, and you just see that any subset of A is closed if and only if it happens to be closed in the bigger space X and contained as a set inside A. And this will have some correspondence in this realm of affine varieties. Okay, so these were the general constructions given a subset, and then there's also given two topological spaces. There's two natural notions. The first is if you're given any map from the first one X to the second one Y, then this map is called continuous if for all Z inside Y closed, the pre-image is closed inside X. Again, you might have seen the corresponding variant of this definition where you require that the pre-image of any open set is open, but just by taking complements on both sides, you immediately get this as an equivalent characterization. And then finally, there is the notion of a product topology. So this is one way to give a topology on a product of two topological spaces. And there, again, here it's more natural to define the open set. So we say U inside X cross Y is open if it is a finite union of products UI cross VI, where UI is open in X and VI is open in Y. And for the affine varieties, we are going to see, interestingly, that the product topology on two affine varieties will not be the natural topology to put on this product. Okay, that's all the recollection for basics of topology.